Welcome to the chapter on disjoint set union, also called union find. This structure keeps a set of items sorted into separate groups. The find operation tells you which group an item is in, and the union operation merges two groups into one. We store the whole thing as a forest of trees inside a parent array, and two tricks, path compression and union by rank, make both operations run in mere constant time. Let's start with why we even need this structure. First, we will look at a simple task that becomes painfully slow with the tools we have so far. Let's look at what you will be able to do by the end of this chapter. The table lists 4 goals. First, you will find a representative. That means you follow parent pointers from any element up to the root of its group. Second, you will update the parent array after compression. You will trace which entries change when a find flattens a chain. Third, you will trace a union. You will predict which root ends up on top when two groups merge. Fourth, you will explain why it is fast. Path compression and union by rank working together give near big O of one time. The main idea of this chapter is simple, and it fits in 3 lines. A partition of elements into groups lives in a plain array. There is no separate tree in memory. Each element stores a pointer to its parent, and each group's root is that group's representative. And 2 cheap tricks keep that array fast. Those 2 tricks are most of the chapter. Think of a big party and everyone's circle of friends. Alice, Bob, and Carol already hang out together. They form one friend's circle. Dave and Aaron already hang out. They form a second friend's circle. Now Bob and Dave meet. Their whole circles merge into one bigger circle. And all day you keep asking the same question. Are these 2 people in the same circle now? Each circle has one representative. To check if 2 people share a circle, you compare their representatives. One new friendship merges 2 whole circles under a single representative. The naive way to answer same group is to run a fresh breadth-first search from one person and see if it reaches the other. Each search costs big O of V plus E with many merges and queries. The work adds up fast. Watch the work pile up. We add edge 0, 1, then ask, are 0 and 2 in the same group? The naive way runs a breadth-first search from 0 up to V plus E steps in the worst case and answers no. We add edge 1, 2 and ask the same question again. Another search from scratch, and this time the answer is yes. We add edge 3, 4 and ask about 0 and 4. A third search from scratch, and the answer is no. And so on. Every single query rewalks everything from scratch. Here is the problem in one word. Nothing is reused. Each query throws away the last one's work and rewalks the whole graph, even though almost nothing changed. Over M merges and queries that is big, O of M times V plus E, and that is the pain this chapter's structure removes. The fix is to keep the answer up to date step by step, and never retraverse the graph. We store which group each element is in, we update it as merges arrive, and we read it off in near constant time. This structure is called disjoint set union, or union find. It answers same group with find. It merges 2 groups with union. Each one runs in near constant amortized time. The earlier million queries drop from about 10 to the 12th steps to 10 to the 6th.